I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics, medicine, nature,
or
Space. Time.
the brain,
Life. The universe.
This week, what actually is a weed? How can you remove body odour from a shirt? And are scientists looking for alien life? It's Q&A time. We've got a panel of scientists ready and waiting to tackle the questions you've been sending in. Hello, I'm Izzy Clark, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First, let's meet the panel. So we've got Howard Griffiths from Cambridge University for your plant ponderings. Howard, the Clare College Gardens are absolutely beautiful. Do you have a favourite plant there?
Yes, I have a favourite giant there. It's a metasequoia. It's a relic of millennia, and it was discovered in China in the 1930s. So it's a wonderful, wonderful tree. It's pretty massive. It's about 30 metres high, I guess.
Oh, wow. Next to him, we've got Kit Chapman from Chemistry World for your chemical queries. Now, this year is 150 years of the periodic table. Have you been to any good birthday parties?
I've been to loads of birthday I've been all around the world. My favourite one has to be the one at St Catherine's College in Cambridge. And there, Yuri Oganessin, the only living person who is on the periodic table, was the guest of honour. And he presented the world's most expensive periodic table, which was fabulous. It was made of gold, silver, platinum. It even had a diamond in it.
Oh, wow, that sounds amazing. Any more lined up?
I'm hoping to get around the world later on in this year. I'm hoping to go to Japan and to Australia as well.
Oh, gosh, lots of parties then. And then next to Kit, we've got Bill College, who's also from Cambridge University. He works on reproductive physiology, so that's puberty, fertility and that sort of thing. How did you start in that field?
Well, I've worked in this field for about 10 years, and I got into it just because we used mice for our studies, and we made a mutant mouse, and it happened to be infertile, so that got me into the area.
Oh, wow. And then where do you go from that?
Well, I also teach it. I teach the undergraduates reproductive physiology, which means that I can give very entertaining lectures and come up with lots of interesting facts that they love.
Brilliant. Got any of them for us?
Yes, the elephant has a prehensile penis, and it can actually control where it goes, so it can actually move around corners, and sometimes it'll use it as an extra leg to rest on like a tripod when it's feeding.
Okay, that was not what I was expecting you to say. Next to myself, we've got Ben McAllister from the University of Western Australia, who's also joined the Naked Scientist team for a few months, and he's here to tackle all things physics. So, Ben, what is your earliest memory of getting involved in physics?
A lot of my earliest science memories in general are from this really great science museum in my hometown, Perth, West Australia, that's called SciTech. And they have this amazing planetarium there that I spent a lot of time in as a wee child, looking up at the dome and the simulated lights above. So that's probably amongst the earliest.
Oh, nice. Over the next hour, we'll be tackling the questions that you've been sending in. And if you want to send in a question to a show like this in the future, then tweet at Naked Scientists, post on our forum, or email chris@thenakedscientist.com. Now, before we dive into the questions, for those of you at home, we've got a little Guess Who quiz running through the show. So we'll scatter clues across the hour for you to guess. And, you know, panellists, you're welcome to join in as well. Here is your first clue. Number 1, the lifespan of our mystery guest is about 20 years and it lives in coastal areas of North America. Who or what am I? Anyone off the bat can think of anything?
I'm thinking it's potentially some kind of large rodent, just based on the fact that it's in South America and, 20 years. It's an animal, one would assume.
North America.
Okay,
it's North America.
In that case, disregard my previous statement.
Sounds to me like it could be a sea mammal or living in estuaries or fresh water.
Okay, well, we've got clues coming up later on the show, so you'll have to wait and see. Now, let's kick off with the questions. Here's one for you, Ben. This is from Dan on Twitter, who says, are scientists looking for alien life?
I love this question. The answer is a resounding yes. We've been doing it for a very long time. At least as early as the sort of 1900s, the very early 1900s, and probably much earlier than that in terms of people just looking up into space and hoping that they see something. But in terms of concentrated efforts using good technology, it will have started around the beginning of the 1900s and really kicked into high gear in the kind of late 70s, early 80s time frame. Broadly, searches for extraterrestrial intelligence, as they are known, fall under the umbrella term SETI, S-E-T-I. Perhaps you've heard of it. And there's a few different institutions around the world that sort of adopt that name and use it to describe the things they do. There are two sort of main types of SETI search, if you like. The probably more traditional one is to essentially get a big radio telescope, kind of like a satellite dish that you would have on the roof of your house, to try and sort of point into space and pick up radio waves coming in that could be signals from alien civilizations. We humans are putting radio waves out all the time, so it's not a stretch to imagine that alien civilizations might be doing something similar. Although there have been no detections just yet, there was at least one really interesting period. In 1977, at the University of Ohio, I believe, they have this telescope called the Big Ear, and it received what is widely considered to be the strongest candidate signal from space for an alien message. It was called the WOW signal. It was basically just an extremely powerful radio signal that hit the telescope once. It lasted like 70 seconds or something like that, some short period of time, and has never been observed again. And no one's been able to explain any source for it. So it's sort of widely considered to be like the closest thing to an alien communication we may have observed.
And so what are people actually looking for? Is it, predominantly just signals, or is there anything more to it than that?
Okay, so the ones with radio telescopes and stuff typically are looking for sort of radio waves from out of space, but there are other ways you could think about searching for extraterrestrial life, and these typically revolve around looking for what are called alien megastructures. So yeah, this is getting a little bit more sci-fi, but it is extremely cool. So we theorize basically that any advanced civilization will constantly be increasing its demands for energy until you reach a point where you basically require all of the energy output by a given star. Like our star that we orbit around, the sun, we don't come close to harnessing even all of the energy from it that hits the Earth, let alone all of the energy it puts out in all directions at all times. But a super advanced alien civilization might want to do that. And if they were going to do that, they would want to build something that we have called a Dyson sphere, which is named after this guy called Freeman Dyson. He was a physicist. He has nothing to do with the vacuums, but
that
fair
was
enough.
My next question.
Yes, no, I thought that as well. I was like, oh wow, but no, definitely not. So the idea behind a Dyson sphere is you basically create some giant structure that encapsulates a star and just like sucks all the energy out of it, like an array of solar panels or something. And maybe instead of having one big rigid structure, you would have a whole bunch of little satellites that orbit the star in rings and stuff and just absorb all the solar energy that way, and then you could have it for whatever purpose you want. And if that was the case, you might be able to see signatures of these things, like Dyson swarms, they're called, these swarms of satellites moving around distant stars. So pretty much every time we see a distant star with like a weird dimming pattern or something, like there's something weird about the sunlight coming off it, some people get pretty excited about the fact that it might be a Dyson sphere or a Dyson swarm or something, but so far there have been no confirmed reports.
Okay, well, thanks very much for that, Ben. Now, from alien life in space back down to Earth, here's one that came into our Facebook inbox, and Howard, hopefully you can help. This says, how do tall trees suck water right to the top of them, and how are some trees capable of supporting themselves so high into the forest canopy?
Well, that's a really great question, and it's one that's puzzled physiologists for many years, and we think we have an answer. I mean, basically, we recognise that trees can be up to 120 metres high. I mean, that's taller than than St Paul's Cathedral dome, for instance. And the reason that water can move up from the soil right through that trunk of the tree and then be lost through evaporation through the leaves is because of the amazing powers of water. It's got this most amazing tensile strength, which it's remarkable, isn't it? Have you noticed how water remains a liquid exactly between 0 and 100 degrees?
Yeah.
But within that range, that's basically why water supports life on Earth, but it's also that hydrogen bonding which holds the water molecules together, which gives it an amazing strength. And then the water rises up capillaries due to two properties known as cohesion and adhesion.
Are they just sort of almost like little tubes that run up and down a tree, essentially?
They're tiny tubes. Most of them are around the diameter of a human hair. Okay, And that's but they act like little capillaries. They're only maybe less than a centimetre, often only a couple of millimetres in length. And so water moves through those tubules, and you can visualise those tubules. They're in the tissues that we call the xylem, which forms the heartwood of trees. And if you take a cross-section through a tree, if you look through a fence post, you can often see the annual rings, which make up the new increments of growth of the xylem that we get every year. So the water is drawn up through that xylem, held by that tensile strength. And then what actually causes it to come right to the top of the tree is the dryness of the air at the surface, at the top, because there's such a change in energy between the free energy of water vapour and the liquid water that's being drawn up through the moist tissues, that when the liquid evaporates into the moist cavities of the leaf and then leaves the leaf to the atmosphere, that draws up more water through those microcapillaries to that site of evaporation within those cells of the leaves.
And even as a tree gets older, does that process diminish? Like, trees obviously can keep going for so long. How can they repair that system if something were to happen to it?
Oh, well, that's another good question. So, partly because they grow new xylem every year. New annual rings represent the new growth. And clearly some very, very old trees don't make very much growth. But what's been intriguing scientists over the last 20 years or so is what happens if those water columns snap. And you can actually hear them clicking sometimes. Now, it's not often you see plant physiologists sort of sticking their ear to the tree, but you can, with a microphone, pick up the sound of those water columns snapping. And we think there are some mechanisms which may help trees, and particularly shrubs and so on, repair those water columns overnight.
How much water does a tree actually need? If you've got your plants in your garden, you're like, I've got to make sure I look after those and they don't die. But how does it work for trees?
Well, for a big tree, like a big beech tree that you might see in a park, they might use, let's say 400 litres of water. So if you imagine 200 large bottles of fizzy drink, that's the amount of water they need every day.
Gosh, that's a lot more than I was expecting you to say. Amazing. Well, thank you so much, Howard. Moving on, Kit, can you help sniff out an answer to this question from European Ocean on our Naked Scientist forum? And for any listeners that are unfamiliar with the forum, it's a great space to share ideas and questions outside of these monthly Q&A shows. So just head to thenakedscientist.com/forum. Anyway, Kit, back to the question. It says here, how can you remove body odour from materials? Certainly a key question as things are sort of getting hotter.
Well, you could set the material on fire. That will certainly get rid of everything. But assuming you want to keep your clothes, let's have a look at what body odour is. So your body will naturally release all kinds of secretions. Sweat is a great example. And the natural bacteria that live on your skin, and everyone has it, it's perfectly normal, they will start breaking those down and release molecules that stink. And they'll react with your nose sensors, and that's how you'll find out that you're a bit whiffy. So when things dry on your clothes, what can you do? One thing is to wash them. Water is fantastic for getting rid of those horrible smells, and also you can use a detergent. Now, detergents are fantastically shaped molecules because they have what we call a hydrophobic tail.
Now, that means that they are essentially afraid of water.
Exactly. So the tail is afraid of water, but the head loves water. So it sticks the tail in those fats, it breaks things up and gets rid of them. That's how we get rid of dirt, and that's why you use washing up liquid to clean your plates. Same kind of principle. So you can get rid of stenches that way. The other thing you can do is try and neutralise them. One thing that works very well is actually using white vinegar in a bowl of water, and that will absorb the smells from the room and neutralise them.
And so why is it that combining that with water, that white vinegar, gets rid of it?
It's not necessarily combining it with the water, it's just making sure that the white vinegar is actually sort of going around the room, essentially. It's because of an acid-base reaction. It's very, very basic sort of chemistry. Speaking of basic chemistry, another thing, and other brands are available, but Febreze is a great example of how you can actually trap these smells. So Febreze has a structure in it called a cyclodextrin, and that's shaped like a donut. It's a big hole in the middle. It's a sort of a circular molecule. And what it'll do is it'll get those molecules in there that are causing the horrible smells inside that circle and trap them. You can't smell it, and the molecules are still there, but the BO's gone.
Oh, Bill, you've got a question.
Yeah, I know some people use sodium bicarbonate to put in the microwave to eliminate smells. How does that work?
We're going exactly the same kind of route as the vinegar. So sodium bicarbonate is a great version of a base, and it will cause that same kind of reaction. So it depends really what the smells are as to how you get rid of them. But sodium bicarbonate, fantastic for cleaning products. And these things are really, really cheap. But everyone thinks that you need to go for a really expensive cleaning product. Actually, wine vinegar, sodium bicarbonate, things that we've used for over 100 years now are just terrific.
Well, absolutely no excuses then. Now, Bill, actually, we've got a question from Lindsay on the forum about fertility and compatibility. She says, I've heard a theory that some couples are incompatible. So individually, they are fertile but can't produce offspring with one person, whereas they could if they had a different partner. Is that true?
Occasionally this does happen. I think one of the reasons is that fertility can be affected by a huge range of different factors. So you might have a couple where they're both slightly subfertile, so that together that's a compound problem. They can't conceive. And then if they split up and they find another partner, the new partner is completely fertile and their subfertility isn't such a problem. So that's one of the possible reasons. Another reason is that in very rare conditions, maybe about 4% of the time, it is known that a woman can make antibodies that will specifically recognize the partner's sperm. So they make antibodies which are released into the vagina when they have sex. The sperm are attacked by the antibodies and it causes the sperm to clump and coagulate. And that prevents the sperm from reaching the egg.
And so essentially they are rejecting it.
They are rejecting it, yes. I mean, I don't think that they have been primed against it or anything like that. It's just that there's this incompatibility, which is unfortunate for that particular couple.
Would there be anything to get around that issue?
Oh, yes, there are ways of getting around that if that is the problem. You can obviously take the egg from the woman and you can fertilize it using in vitro fertilization in a dish, and then you can take the fertilized egg and you can implant it back in the woman. That means that there's no antibodies in the dish, so it should work fine.
And Kit, did you have a question?
Yeah, I'm just curious as to whether or not someone will be attacking every sperm, or is it just a specific person's sperm, or is it a specific group of people's sperm?
It's related to a person's sperm. So if they have this problem that they make antibodies against a particular sperm, it'll be all of the sperm from that person, and it necessarily won't be from another person. So it's not selective. It'll be all of the sperm that are attacked.
And how important are hormones when it comes to fertility?
Hormones are very important in fertility. So in males, for example, testosterone is absolutely crucial for fertility. When you go through puberty, your testosterone level rises, and that's required to start making sperm at puberty. And anything that reduces your testosterone after puberty is going to impact on your ability to make sperm. And there are lots of things that could impact on your testosterone levels. One thing is that if you are overweight and you have a lot of fat tissue, then testosterone is lipophilic. It likes lipids, which fat tissue is. It'll tend to get sequestered into the fat tissue, which can result in lower levels of testosterone in the bloodstream, which can have an effect on how well you make sperm.
I see. Now, Howard, how about plants? I mean, what determines how many seeds a plant makes?
Oh, well, that's a big question. Well, it depends what sort of flower it makes. Sometimes plants make a single flower. They have a kind of a determinate structure to their what we call their inflorescence. Sometimes when they start flowering at the bottom and they just keep flowering, like wallflowers at the moment, that's called indeterminate. So they can have lots and lots of seed production, pods and so on. That's partly the condition. It also depends on whether they've got enough water and nutrients. So plants can adjust their structure, the number of branches they might have, the number and size of the flowers they have, if they've got plenty of resources, and that's all controlled by the similar substances to the animal hormones. We call them plant growth substances. And then finally, it decides whether they need to allocate reproductive effort into seeds, or sometimes you might have other storage organs. So take the potato, for instance. We know that they store a lot of resources underground because they reproduce from that vegetative structure. It depends really how you're going to produce your generation in the following year, whether it's from a seed or whether it's from a vegetative structure.
Well, thanks very much, Howard. Still to come on The Naked Scientists, what actually is a weed? Is there a male contraceptive? And why is printer ink more expensive than gold? We've also got a game of Guess Who running through the show. First, we heard that our mystery guest has a lifespan of about 20 years and lives in coastal areas of North America. And clue 2 is that adults eat crickets, ants, small beetles, grasshoppers and spiders. What do you think it could be? We will reveal everything later on. Now, usually we talk about misconceptions on the show, so this is common myths that can be debunked by science, and our lovely panel have brought in their own with them. So let's start with you, Ben. What are you putting on the table?
Right, so mine is actually more of a science history myth than a science myth itself. I figured, given that I'm here to represent the physical sciences, I might confront a common myth about one of the most famous physicists of all time. You may have heard the idea that Albert Einstein supposedly failed some maths tests in school, or maybe it was in university or something. And yeah, that's not really true. He was something of an unconventional student. There is a bit of truth in that. He didn't get along well with his teachers. He didn't like the way things were normally taught. He had a tendency to sort of not pay attention in school. But all signs point to him doing maths quite well at all times, which probably makes a fair amount of sense if you think about the career he went on to have. But the sort of origin of the myth is that when he did try and get into university, he did fail his entrance exams, but it was not because he failed the maths section. It was because he failed the botany, zoology, and language sections. So perhaps someone here on the panel could have helped him out there. But yes, in the meantime, he was alone.
Do we know where it sort of came from, or is it just one of those ones that's just floating about?
Yeah, I think it probably just spawned out of that, the fact that somebody read somewhere, what, he failed his entrance exams into university, and then wanted to create some kind of pseudo-inspirational myth surrounding it, you know, which is, I mean, it's a nice story. It's the idea that, like, Albert Einstein, one of the greatest physicists of all time, failed his maths. So if you're bad at maths, you might be good later, I guess is the message. I don't know. But yeah, something like that.
Yeah, if anything, went on to be a very, very important person for the world of physics and maths. Okay, so Howard, what are you putting down as a misconception?
Okay, what really gets me wild is when I hear regularly on TV and radio programmes that the rainforests are the lungs of the earth. Now, don't get me wrong, I think trees are absolutely vital. I want to plant more trees. I want to stop people cutting down forests because forests are absorbing carbon, they're protecting us against climate change. But when that phrase is used, it's often used to infer that the oxygen we breathe is being produced at this minute by the forests. And what you've got to remember are that forests are really giant compost heaps. There's as much rotting, degrading and material just being respiring and consuming oxygen as there are in the photosynthetic leaves above, which are producing oxygen. So there's roughly a net balance.
Okay, so do you know where the majority of our oxygen comes from?
Well, it did come from plants. It's come from plants both in the marine system and on land over the last 2.4 billion years. And gradually, organic carbon made by plants has been buried either underground in the sediments turned into rocks and so on. And that's trapped carbon. Some of it's turned into fossil fuels, which, of course, we're now burning and releasing CO2 back to the atmosphere. But that's where the carbon went, and that allowed the oxygen to gradually increase in the atmosphere.
Well, thanks very much, Howard. Now, Kit, what are you putting down as something that gets on your nerves?
This myth that you can't turn lead into gold. You absolutely can do that. You don't want to do that, but you can do it.
How would you do that?
Well, in 1980, there was a very famous chemist called Glenn Seaborg, and he was a nuclear chemist. And what he did was he got a particle accelerator and he fired carbon and neon atoms at a piece of lead and chipped off some protons. And protons decide what element you have, and he bashed it way back down into gold.
Right, why aren't we all trying to make gold then?
This is the problem. So to fire it up a particle accelerator is a bit expensive. It cost him around $120,000 a day to do it.
A day? Wow, okay.
So he worked out that to make 1 ounce of gold would cost $1 quadrillion.
Come on, guys, we can put that down together, no?
It seems like something we could scale as well. I mean, maybe it costs that much today, but we'll push that down in time if we all put enough effort into it.
Bill, how about you?
Well, this is a sort of myth that I'd like to debunk, which is aimed at couples that are trying to conceive. And people are told that if you're trying to conceive, there's a window of fertility, which is the best time, around the time of ovulation for the woman. And if you're having sex around that time, you should have intervals. You should have sex every other day. And it was thought that this is to allow the sperm to build back up to increase your chance of conception. And actually, it's completely not true. The best way to conceive during this window of fertility, the window of opportunity, is to have sex as often as you can, provided you're up to it, of course. And the reason that we now know that it's best to just have sex frequently comes from IVF clinics, where men have gone in, they've given a sperm sample, and then they've taken another sperm sample 2 hours later, and often the second sperm sample has more sperm than the first. So basically, you can just have sex as often as you want during this fertile period, and that will improve your chances of conception.
Do we know why that happens, that, a few hours later there is a higher sperm count?
Well, we make a lot of sperm very, very rapidly. I think that, we're making 5,000 sperm every second as we are, I'm afraid. You're not.
Yeah, I'm not.
But men are making 5,000 sperm or so every second. So we're making millions of sperm over a few hours. And I think what happens is that the first time you make sperm, there may be some there that has been sitting around for a while, whereas 2 hours later, it's sort of fresh stuff. So they're much more virile and much more potent.
We talk about this ovulation period, the golden opportunity, 6 or so days a month. Can a woman get pregnant outside of that period?
So there is a reproductive window during which a female is likely to get pregnant, and it lasts for about 6 days. The reason it is such a short window during the whole of the cycle is that an egg's only viable for about 12 to 24 hours once it's released. Sperm cells are a bit more robust. They can be viable in the reproductive tract for up to 5 days. So if you put these two together, you've got a window of about 6 days when you're more likely to conceive. And outside this window, you're ultimately much less likely to conceive. And women often use this natural sort of rhythm method to monitor when they're going to ovulate and to make sure that they don't have sex close to that period.
And we're going to get to contraceptives later, but is that a reliable method of contraception?
It's not the most reliable method of contraception. I think if you use that method, you have to be prepared for failure some of the time. There are more reliable methods.
Now, let's dive back into the questions. Ben, this came from Hans on the Naked Scientist Forum, and he asks, are all the planets in the solar system the same age?
This is another great question, and the answer is yeah, pretty much. Within a narrow window, within the degree of confidence we have in saying a date for any of these things, we're pretty sure that the entire solar system, the sun, the Earth, most of the planets, all of the planets, are something like 4.6 billion years old, again, give or take a few million years. So this is a very sort of a large number type problem that we're dealing with here. The easiest one, the first thing that we can do is basically just date rocks on Earth. We can use geological processes and radioactive decays in order to figure out how old rocks are on Earth. And that's easy to do because we have rocks on Earth kicking around all over the place. So how you might do that is if you pick up a rock that's you think is one of the older rocks on Earth, maybe it's deep down in the core. I'm not entirely sure where the oldest rocks on Earth actually come from. But if you were to find one of these old rocks on Earth, you could look at the relative populations of these different, what are called radioactive isotopes inside them. So there are these sort of natural chemicals that undergo this process called radioactive decay. We were hearing a little bit about it before, sort of turning one element into another element by stripping off a few protons. So there are things like uranium, which break down into smaller things, and they sort of do this with a characteristic time associated with them. There's a bit of variation, it's a bit random, but for a very large population of, say, uranium, there's going to be a certain amount of time with which about half of that uranium breaks down. So if you look at a bit of rock and you can figure out how much uranium is in there, and you also look at, for example, how much of the stuff that uranium breaks down into is in the rock, you can sort of figure out how long ago that decay started happening by knowing how much uranium there was originally and how long it takes to break down, and then you can date the rock. We can do a similar process with rocks from the moon, because we've been there. We can do a similar process with sort of bits of rock that have landed on Earth that we're pretty sure have come from Mars at some point in the past. So basically we've got Earth, the moon, Mars that we can directly access, and then you can look at the other planets and you have to do a slightly different process to figure out how old they are because we don't have any rocks from Jupiter or anything.
So how does that work?
One of the best methods that people use to figure out how old something like Jupiter is basically looking at the surface of Jupiter and counting how many craters there are. Because one thing that we are pretty sure about is that the number of stray bodies moving through our solar system that collide with the planets has been pretty constant over a really long period of time, billions of years. So if we know how many craters there are on something like the Earth or the Moon, that we're pretty confident in how old it is, and we compare that with how many craters there are on Jupiter, just because we can be pretty sure that the sort of relative rate with which they're being struck by stuff is the same, we can infer the age of something like Jupiter or one of the other planets in the solar system.
Brilliant. So, Hans, there you have it. I mean, I guess it also depends on what you're using as a reference of a year, because someone who is 30 in Earth terms is also 120 years on Mercury or 2.5 on Jupiter. So we'll say Earth years.
Yeah, also, if you use the kind of uncertainty that we have in dating planets, they might be 1 million years old or they might not have been born.
Brilliant. Now, Howard, this was posted by user Soya on the Naked Scientist forum, and she asks, what actually is a weed? And then continues to say, can anyone give a complete definition? Because it appears to me at the moment that most gardeners say it's basically anything I don't want to grow there. Is it as simple as that?
Well, I think you've really answered your own question. But just to explain, I mean, beauty is in the eye of the beholder. And if you're a naturalist and wandering through the countryside, many of the natural plants you see would be classed as weeds if you found them growing in a cultivated border. Equally so, you might see plants like invasive aliens, like Japanese knotweed or a giant hogweed or something like that. And you might think, that's a weed of the countryside. We need to get rid of that one. So it really does depend where those particular plants are. I do remember as a child being told a joke, which I don't think is a very good joke, but it said, it asked, how could you tell whether a plant is a weed or a border plant? Is you pull them all up, and the ones that regrow are the weeds.
Very true, because they're really hard to get rid of. You can spend so much time pulling them out and thinking, great, got that one done. And then, give it a couple of days, it's back again. So how can you actually get rid of them?
Well, I'm not a great believer in using chemicals and sprays, although, of course, you can use those very selectively and very carefully if you paint them onto individual plants, and some of them be taken down into the plant and kill the actual deep roots that are the ones from which the plant will regrow. I'm a great believer in weeding and hoeing and using rather traditional methods of weed control.
And speaking of annoying things in the garden, as a bit of a follow-up, it seems to be on everyone's mind at the moment, Emma has also got in touch to say, how on earth do mealybugs and other bugs grow on plants, and where do they come from? Are these those sort of small green bugs that we see on plants that we actually don't want there?
Yeah, well, mealybugs are a kind of a scale insect. They're rather similar to aphids in that they're a slightly different sort of class of organisms, but they have similar penetrating mouth parts which dip into we talked earlier about the water conducting system of plants. This is the sugar conducting system of plants. So they dip into the phloem and they feed on that. And that's why they often exude droplets of honeydew, aphid honeydew, which you may hear of. So where do they come from? Well, they overwinter in cracks and crevices or in the soil, or they may be laid down as packets of little eggs from which the new instars will germinate once the cold weather has gone away.
And are they a problem for plants?
They're a real problem for plants, not only because they take out their feeding on some of the sugars that the plant's trying to supply to its growing areas, but they also transmit lots of diseases. Lots of viruses are transmitted through these sap-sucking insects. And there's some very interesting science being done by my colleagues which show how even the viruses change the behaviour of the insects in order to make them move on and move to another plant and so on. So
goodness. So is there anything you can do to get rid of them?
Well, again, I'm all in favour of using warm, soapy water to wash them off, or gently going along and squidging the black fly on my broad beans with my fingers. I'm afraid it's a bit messy, but you can use safe sprays available from garden centres and so on.
Bill, what would you like to ask?
When I was doing biology at school, my biology teacher told me a story, and I'd just like to know if this is true. Scientists wanted to know what the composition of the sap was from the phloem, and you mentioned the aphids tapping into it. And he said that what the scientists did was they took aphids and they chopped off effectively their head and left the bit that was in the sap. And they collected the droplets of sap coming out and they analysed it. And that's how they did it. Is that correct?
There's some fascinating videos available on YouTube which can show scientists excising aphid stylets and collecting the sap as it drips out. The very clever trick that aphids have learnt to do is to plumb into the phloem without it blocking. If you artificially try to put a needle into the phloem, it will automatically coagulate and block and prevent the sap from flowing. But the aphids have learnt how to circumvent that problem.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
This week on The Naked Scientist, a panel of experts are tackling the questions you've been sending in. Those experts are physicist Ben McAllister from the University of Western Australia, Howard Griffiths from Cambridge University for all your plant ponderings, Kit Chapman from Chemistry World for, you guessed it, your chemical queries, and Bill College, also from Cambridge University, to cover all the things on reproductive physiology. And if you want to ask a question on a future show like this, then you can send it on over. Tweet us at Naked Scientist, find us on Facebook, or post on our forum, thenakedscientist.com/forum. And we have a question for you at home. We've been playing a game of Guess Who throughout the show. First, I told you that our mystery guest lives to about 20 years old on the coast of North America. Adults feed on insects and spiders. And clue 3 is our mystery guest is internationally listed as vulnerable. It's also under consideration for the federal listing on the US Endangered Species list. This species is threatened by overcollection, habitat destruction, and fire suppression. It's now quiz time. As promised, we have a little quiz for our panel. You can also play along at home. Don't look so worried, everyone. It's going to be okay. Team 1 is Ben and Howard, and Team 2 is Kit and Bill. There are 3 rounds. Round 1 is more or less. So, Ben and Howard, does a bee hummingbird weigh more or less than a 1p coin?
A bee hummingbird. Now, that's interesting. I would think there would certainly be types of hummingbirds that weigh more than a 1p coin.
But I think from the sound of a bee hummingbird, I mean, to be or not to be, that is the question.
Okay.
That is indeed.
So I would say
it's a trick
could
question.
weigh less.
Yeah.
I would say.
Okay, but really, I'm a colonial, I must say, so I haven't got a lot of experience with 1p coins, but can you really fathom a bird that weighs less than that?
I'm going to have to hurry you. What's
Okay.
I would say yeah.
Okay, I'll go with the biologist here. Let's go with less
So-
then.
It weighs less. Hey, congratulations. A 1p coin weighs 3.56 grams. A bee hummingbird, which are found in Cuba, on average weighs just 1.8 grams.
Wow.
So, yeah, well done. Kit and Bill, over to you. How do you feel on quizzes? Are we good at them?
Well, I was on the worst scoring university challenge team of all time, so no.
So, positive.
I did win a quiz at school once.
Okay, so let's see how you get on. Team 2, Kit and Bill. Is the height of the Elizabeth Tower, which is home to Big Ben in London, more or less than the height of the tallest redwood tree in California?
Wow. I mean, the redwood trees grow pretty big.
Yeah. I mean, my gut instinct here would be to say the tree's bigger.
Yeah, so I think the biggest tree is called the General Sherman. I might be wrong with that. And it's a fair old size, so I think the tree is probably bigger.
So you're saying that redwoods are bigger?
Bigger.
Yes.
Correct. Redwood trees are the tallest trees in the world, the tallest being 116 metres tall. That's 380 feet. And the Elizabeth Tower that's home to Big Ben is just 96 metres. Right, so over to round 2. This is called Animal Magic. Ben and Howard, what do you call a group of flamingos? Is it A, a fiend of flamingos, B, a flamboyance of flamingos, or C, a fortune of flamingos?
I feel like any of them are appropriate, but I might have said something like a festival of flamingos if if it was up to me. I like flamboyance.
Yes, it sounds reasonable to me. I'll go with that.
Yeah. Unless do you have any leading?
No, I have no idea whatsoever. I'll go with you.
I'm going to go with the flamboyance of flamingos.
Bill, you can't give a thumbs up to get the hell you're supposed to be the other team.
He'd already got the right answer.
Well, let's hear it. Correct.
Hey, 2-2.
Okay, well, Team 2, Kit and Bill, similar question. What do you call a group of ferrets? Is it A, a bulk, B, a band of ferrets, or C, a business of ferrets?
Well,
I think I know this one.
oh, great. Well, you were on University Challenge, so I'll let you make the decision.
Oh, don't say that now. Go, what are you going to go for?
I've no idea. Probably the last one.
A business. I think it is a business of ferrets.
Oh, very well done. Yep, it is indeed. And we actually had a lot of fun in the office exploring this. You can also have a conspiracy of lemurs, a smack of jellyfish, a kaleidoscope of butterflies, or a leap of leopards. But I digress. So let's go on to round 3, which is true or false. So back to team 1. We're all to play for on this round. Ben and Howard. True or false, there are more people that have lived on the International Space Station than there are elements in the periodic table.
Oh, okay. That's a great question. So I was going to be like, International Space Station, there's not that many, but there's also not that many elements. It's like 100 and something and change.
Is that 117, 120,
Yeah.
is it? So how well...
I would think there haven't been that many people living on the ISS.
I would imagine, because they tend to stay there for quite a long time
Yeah.
once they've been put up into orbit, and they've had a limited number of shuttles that have been able to deliver them and bring them back. So
No, I
should
think
we go for less?
Yeah, less ISS than elements in the periodic table. Yeah, okay, let's go for it. That's false.
False.
Is what we're assuming.
Yeah,
Yay!
there
3 for 3.
are.
Feeling
You're very
good.
well
Ooh.
done. There are 118 elements on the periodic table, but only 109 people have lived on the International Space Station. I was hoping
Narrow.
to catch you out with that one. Okay, true or false? Team 2, Kit and Bill. The total length of blood vessels from the average person is enough to go around the world 2.5 times. True or false?
What do you think?
You're looking at me, right?
I'm
As a
absolutely looking at
physiologist.
you as the physiologist.
This is like watching a penalty shootout, isn't it?
There's a lot of blood vessels.
There are a lot of blood vessels. I'm going to have a guess. I think it's true.
It is true. An average human has 100,000 kilometres of blood vessels, and the Earth's circumference is 40,000 kilometres. Well done. Right, so that means it's over to a tiebreaker. Closest wins. How many patents did Thomas Edison get in the US? Team 1, have you got an answer, do you think?
We're going to guess 175.
175. Team 2?
Should we go 176?
Shall we go? Let's go higher.
Let's go 400. Should we go? Should we?
402.
Well, I can announce that Team 2 are the winners, but you are quite far off. It's 1,093.
Wow!
He had 512 worldwide patents, but over 1,000 just in the US. And Shunpei Yamazaki has over 5,000 patents in the US now.
Goodness me.
Yes. So congratulations, Team 2. You are our big brains of the month.
Thank you.
Kit didn't do the best on University Challenge, but you've won our monthly
A
quiz.
much higher prize. University Challenge.
Let's dive into some more questions. This is for you, Kit, from James on Facebook. And he asks, why do so many chemical reactions give out heat or explode? Where is that energy coming from?
Well, the energy isn't actually coming from anywhere. Energy, we don't make energy. If you know how to make energy, contact me. We'll win the Nobel Prize. It'll be fantastic. Energy is just transferred. What's happening here is we're transferring it from the chemicals themselves out into the atmosphere. So when you have a chemical reaction, this is what we call an exothermic reaction, something that gives off heat. And what you're doing is you're breaking up the bonds. So if you think about it, you've got your molecule, that's atoms attached to each other with bonds. Those bonds have to be broken and reformed to make whatever you're making. And so when you break those bonds, you're releasing the energy there. When you're reforming the bonds, that takes up less energy usually. And so that means that there is energy left over, and that's given away as heat.
Over to you, Bill. And we've talked about pregnancy, but what about preventing that situation altogether? We've received this question from Sophie, which says, how does the pill work and why has it taken so long to get a male contraceptive?
The modern pill that females take actually prevents pregnancy in two ways. It contains two hormones, usually. It's a synthetic estrogen, which is a female hormone, and also a synthetic progesterone, and they work in different ways. So the estrogen component, what that does is it causes a thickening of mucus within the reproductive system, and that makes it more difficult for the sperm to reach the egg. The progesterone part of it acts slightly differently. What that does is it suppresses the reproductive axes and prevents ovulation. So there's this dual effect. You could get by just with estrogen only. You don't have to have progesterone. But it's a bit like belt and braces. You've got both actions which will make the contraceptive much more effective. But it's been a lot more difficult to make a male contraceptive. And the reason for this is just the way in which the body works and the difference between men and women. So if you think about women, they go through cycles and they produce an egg once through it out a 28-day period. Whereas men are making sperm continuously. And it's much more easier to suppress one egg being released at one point in the cycle than it is to suppress the millions of sperm that are being made continuously by the men.
So have we got to a stage that we can now have something similar that would work for men?
There's developments that are going on. Ideally, what you want is an oral contraception for men, just like for the woman takes the pill and it gets into the body. Theoretically, you could give men analogues of testosterone and increase the testosterone levels, which eventually would suppress sperm production. The problem with that is you can't take it orally. You ingest testosterone and most of it gets inactivated in the liver straight away. So you have to inject it, which means that every week you have to have an injection of high level of testosterone. And most people wouldn't use that as a contraceptive. So that's how it would work. But it's not possible to take it orally at this stage.
And do you think there will be developments to get something like that, or are we still not quite there yet?
There are developments aimed at having an oral contraception. One of the problems, of course, is that it has to be reversible. Yeah. If someone stops taking it and then wants to conceive, there's no point in having all of your germ cells dead in your testes. So it has to be reversible.
Absolutely. Bill, thanks very much. Throughout the show, we've been running this Guess Who game. And it's time for the fourth and final clue. So the first clue I gave was that the lifespan of our mystery guest is about 20 years and lives on the coastal areas of North America. We then heard that adults eat crickets, ants, small beetles, grasshoppers and spiders. Clue 3 was that our mystery guest is internationally listed as vulnerable. And our fourth and final clue is... it grows in moist, acidic soil and is one of the very few plants that uses motion to actively trap its prey. Has that thrown a curveball? Do we think we know the answer, dear panel?
I think we know the answer, don't we?
Howard has to give the Latin name.
Would it be Dionea
Oh, yes.
muscipularis?
Oh, we'll take it. Yes, it is. It is a Venus flytrap. Well done to anyone who else got that at home. And do tweet us if you did, and we'll give you a shout out in our next monthly Q&A.
Can I just add that it's actually found growing in a really very narrow part of the eastern seaboard on the border between North and South Carolina in these very sandy dunes that are hit by fire.
Yes, I was worried that if I'd said it's in North and South Carolina, that would instantly, knowing you, Howard, would give the game away completely. But yes, you are absolutely right. Now, we've just got time for a few more questions. So, Ben, this is from Sam. What are the pros and cons of using nuclear power?
Okay. There are two primary types of nuclear power. I'll very quickly run through both of them. We already heard from Kit before that we can't just create energy out of anywhere. We have to get it from somewhere else. In the context of nuclear power, we are making use of a very famous relationship that was first I guess you'd say discovered by a person I mentioned before, Albert Einstein, with this very famous equation E equals mc squared, which tells you that the energy that a given thing has is essentially equal to its mass times a constant, the speed of light squared, which is really just a way of saying that mass, how heavy something is, if you like, is just another form of energy. So if you can change a thing's mass by changing, well, we'll get back to that, then you can harness some energy by sort of breaking off a little bit of mass and converting it into energy. And the amount of energy you can get out is really, really, really big. In the context of nuclear power, what we're doing is essentially taking, well, I mentioned it as well before with uranium and elements that can break down and become other elements. You're taking something, for example, big, like uranium, and it has a certain mass. A uranium atom has a certain mass. It breaks down into two smaller atoms. But when you look at the mass of those two atoms combined, it doesn't quite add up to as much as the uranium atom that you started with.
So you've lost a bit.
Well, you haven't lost it. It's just converted into energy and it's radiated away. And that's sort of the fundamental principle of what's called nuclear fission power. And that's what goes on in, well, all nuclear power plants that actually generate energy in the world today. You could also theoretically make use of another nuclear process that works in a similar way, which is called nuclear fusion. And that's what the sun does when it wants to make energy. So what you would do with nuclear fusion is you'd take a light thing, like hydrogen, the lightest element, and you'd smash a bunch of hydrogens together until you got a helium, which is the next lightest element. But again, the mass of that helium atom is going to be slightly less than the mass of all the hydrogen that you put in, so you get a bit of energy released. And the sort of pros and cons of these things, well, if you're talking about nuclear fission, which is the one that we know how to do, again, there are no fusion plants on Earth yet, although we're getting there. The sun is an example of one. You take a nuclear fission reactor and you break down stuff like uranium. The great thing is you don't produce a lot of carbon dioxide, you don't produce a lot of other harmful greenhouse gases, and it is pretty good for the environment in that way. The cons are you can produce a lot of radioactive waste. Personally, I actually think the amount of radioactive waste that you produce is pretty acceptable from modern plants compared to the kind of toxic stuff you put out from every other kind of energy production that we use. It's just kind of, you've got to put something out. And the other con is that there is the possibility for essentially huge disasters. Like you may have heard of the Chernobyl reactor meltdown. There was Fukushima in Japan a few years ago, where the reactors essentially run away. They generate this so much energy and they create what's called this chain reaction that runs away and you can't control it, and they just keep putting out so much energy and they melt down.
Looking at nuclear fusion, though, are we close to getting anywhere near being able to do that process?
Nuclear fusion is difficult because you essentially need to create conditions similar to the sun, which means you need very, very high temperatures. You need to have things very, very close to each other, very condensed, very high pressures. So we have been able to make nuclear fusion reactions happen on Earth. It's just that we haven't been able to do it in such a way that we're getting out more energy than we're putting in, and we're able to keep them sustained for a really long time, which is what we would want to do if we were going to build a reactor, essentially build like a small sun. If we could do it, it would be great, because nuclear fusion will get around, well, basically the two biggest problems associated with nuclear fission, whilst also still producing no CO2. The first one being that there's no toxic waste, or a very, very small amount of toxic waste produced. The main byproduct from a nuclear fusion reactor is helium, which is really inert. It's not going to do anything to the environment. And in fact, we actually need it to do other science. It's a thing that we need and we're actually running out of. So if we could make a bunch of it as a byproduct of creating energy, that would be kind of cool. The other thing is it's very, very hard for a fusion reactor to melt down. So we can kind of reduce the danger there as well.
Well, Ben, thanks so much. Now, Howard, we've had this question from Sarah, who says, why did my daffodils flower in February this year and are now dead already? I can relate. We're based in Madingley in Cambridge. There were beautiful daffodils everywhere. It's getting warmer and now they're all dead.
Well, it just shows what clever things plants are, because they always find a time and a place to be able to flower and produce seeds. And so the key thing to do is to wait, and they'll come back next year. Because what they're doing at the moment with the leaves is they're now making reserves that they're storing and putting back into the bulbs that will sit out and allow the plants to last right the way through maybe a hot, dry summer in the Mediterranean, maybe a hot summer here, or maybe the shade of a forest canopy over and above. So when we're talking about bluebells, for instance, bluebells are just about to start flowering, they have a similar response. These plants are called vernalized plants because they flower in the spring. And sometimes we have equivalent ones that flower in the autumn crocus, for instance. So they avoid competition from either environmental conditions or shade by flowering out of synchronization with the main growing season for other plants. So they're vernalized plants. But one thing I would counsel is when your daffodils have finished flowering, don't cut the leaves off.
And why is that?
Because those leaves need to be carrying on making sugars to store, to put back into the bulb for next year.
Right, over to you, Bill. We've received this question from Charles on Facebook, and he asks, are children going through puberty at a younger age? Are they?
Yes, they are. If you look historically at the age at which particularly girls first start going through puberty, and usually this is measured by their first period, in 1850, let's go back to 1850, it was about 17 years old. By 2010, it's 12 years old. So there's definitely been a decrease in the age at which children go through puberty.
And do we know why that is?
Well, partly this is caused by better nutrition. So people are better fed now. Certainly from 1850 onwards, we've got better nutrition. And what is happening is that people are growing more rapidly. They're gaining a critical body mass, and you have to achieve a critical body mass to go through puberty. But importantly, it's not just about how much you weigh, it's about how much fat you carry in your body. And it's thought that you have to have about 17% of your total body mass as fat to go through puberty, and you've got to have about 22% of your total body mass as fat to maintain fertility. And if you fall below those, you either won't go through puberty or you will become subfertile. Top athletes that have less than 5% body fat, the females often don't cycle. They don't menstruate. They're infertile because they have less body fat. So what we think is happening with the Western diet, of course, children are perhaps becoming obese. They're carrying a lot of body fat at a much earlier age, and this means they're actually going through puberty at an earlier age.
Does that impact your life later on?
It can do, yes. It can increase the risk of developing certain types of cancer, ovarian cancers, because as soon as you go through puberty, you start making all the various female hormones, and you're having a longer exposure to those over your lifetime. So it does increase the risk of some types of cancer.
Well, thank you for explaining that one, Bill. And finally, Kit, we've received this weighty question from David, and he wants to know, why is printer ink, weight for weight, more expensive than gold? Is that true?
Well, it is true, but bear in mind that gold is a really dense and heavy thing. So if you think about a pound of lead and a pound of feathers is going to take up far more space. But gold is not the most dense element. That's actually osmium. But it is dense, so it takes up very, very little space, and that's why printer ink seems to be more, because you get far more bang for your buck. But printer ink is not the most expensive substance on Earth. That's a common misconception. The most expensive is californium. And this goes back to what we were talking about earlier with nuclear reactors and making things. What we actually do is we stick rods into our nuclear reactors. There are 2 of them that can make californium on Earth. One's in Russia, one's in Oak Ridge in Tennessee in America. And it undergoes a series of what we call neutron capture reactions. A neutron gets turned into a proton, and that moves it one place up the periodic table. Eventually we get to californium, and that's really useful for things like space probes and exploring Mars.
And there we must leave it. Thank you for listening and for sending in your questions, and thanks to our panel. That's Ben McAllister, Howard Griffiths, Kit Chapman and Bill College. And before you leave, we have a quick message.
I'm a few years into my career now, and I thought it would be a really neat way to start to specialise in something that I felt passionate about, that I really enjoyed, and it'd be learn skills that really complemented what I was already working on in my day-to-day life.
I wanted to invest in myself and my future career, and I leave every session full of inspiration ideas that I can put into practice every day at work.
I was looking for a way to give myself some background to what I had already started practicing. So I had kind of gone into science communication a bit already, and I wanted to make sure I was doing it right and doing it well.
We did a session on science and policy, which was particularly relevant to my job, so I found that one really, really interesting.
So now I started a new project on YouTube and social media regarding neuroscience. So I'm going to apply what we have learned about video editing, content, and also the theory.
Interested? Then why not come and join us and sign up for our practical science communication course at Cambridge University. It's part-time. It's aimed at anyone who wants to understand how we communicate and how we can communicate better across all types of media. You'll learn to put theory into practice, and you'll earn a qualification in the process. For more information, go to nakedscientist.com/course, but don't hang around because the entry deadline is not far off.
So get to it. And if you're a fan of the show, why not leave us a review? We love hearing your thoughts and feedback about the podcast. That's all for this week. Do join us next time when we'll be exploring dark matter. What is it and why does it actually matter? The Naked Scientists come to you from Cambridge University and is supported by the EPSRC and Rolls-Royce. I'm Izzy Clark and thank you for listening. Goodbye.